great. Two-dimensional motion. If we're going to talk about 2D motion, we need to obviously have some idea of what a dimension is. Left versus right. Is that a dimension?
No.
On a 2D, yes.
No. Left versus right. Left and right are not two dimensions. I should ask that better. Is left versus right, are those two dimensions? No. That's the question I should have asked. Left and right is one dimension. It's one choice. You can either go to the left or you can go to the right. You can't go both at once. That's one dimension. What about forward, backward? One or two dimensions?
One.
Just one, only one choice. Up or down? One dimension. So we have three dimensions. So that's 3D. We're going to be stuck in 2D, meaning we're going to think x-axis and y-axis. Our x-axis will be our x-axis, our y-axis will be our y-axis. We just need to be very careful to keep our stuff organized into the appropriate side, into keeping everything okay. So the first question we're going to do, let's see where the edge of my board is a river. How wide should this river be?
12 centimeters.
That's insane. 12 meters. Let's make that a little bit, let's say 36 meters. 36 meters. It's a reasonable size, it's about 100 feet. Okay, so we got a river. That boat is at the dock, it's at rest, it's not moving yet. It's going to start from rest, it's going to turn the motor on. Well, motors cause a force. What do forces cause?
Motion. A change in motion.
Change in motion, they cause an acceleration. This acceleration, we'll say, is 2 meters per second squared. And the question that I would like us to answer is, how long does it take the boat to cross to the other side of the shore? How long does the boat take to cross? Now, when I write how long, you should instantly know what that means. Time. How long does it take, I'm supposed to add in, to cross? So we're trying to look for time. Let's think way back to kinematics. This was like 18 years ago. Let's think way back. How do we start every single kinematics problem always?
Writing what you know.
Writing down what we know. List our variables. Because the whole thing with kinematics is you got to pick the right formula. And that's what people really struggle with, which is understandable. The whole thing is picking the right formula. So you got to make a list. And your list has to have the right stuff. And then you find the equation with your list. What direction is the boat going in? The Y or the X?
Y.
It's going in the Y direction. So we're going to label our little given chart with the Y axis. So, what do we know? We know the acceleration. Which acceleration is this? A or X or Y?
Y.
It's in the Y direction. So I'm just going to label it with a little A subscript Y. Nothing fancy there. I don't remember if I actually said this or thought it, but it starts off at rest. It starts off at rest. It's not moving at the beginning. Then we turn the motor on and it starts accelerating. So what else do we know?
Initial velocity.
Which initial velocity?
Y.
The Y. So we have, again, the double subscript. Now, let's look very carefully at this. There are multiple ways that you can write this. Only some of them are correct. It is not void. It is not void. Girls with the big handwriting, stop writing this. It is not void. Oh, the not and the Y are subscripts. So we have subscript, subscript, or like subscript and then a subscript of a subscript. Either of those things works.
I have a question.
What's up?
On the formula chart, is this where it comes in? Like you have, it's like
Yes.
Y.
This is why the formula chart has all those billions of subscripts. Because now you have to choose which direction you're going to do. We're choosing Y direction. We're going to come right back to that question in just a second. What else do we know? We know one more thing.
Final.
Not so much. Distance. And instead of distance, I like to use the word displacement instead. What's next? Is it X though? It's delta Y. Because we are now going a certain distance in the Y direction, not the X direction. So now we have two different things for displacement. We have delta X and we have delta Y. It is a little confusing, but all of them have X and Y. Your acceleration will now either be AX or AY. There's nothing weird or fancy about that. You just do it and move on. Yes?
Okay, so we always go what it looks like on the paper because, like, in reality, the boat would be going down.
You stop talking right now. We know some Y stuff. We know some Y stuff. What are we trying to find? Don't worry about it. We're trying to find the time. We will come back to that, but I don't want to be there right now. It's a scary, scary place. Okay, we're trying to find the time. How are we going to find the time? Guys, focus. I promise we'll come back to that. How are we going to find the time here? What is the next step conceptually from doing this problem?
The equation.
We have to find the equation. Find which formula, right? Is there some magic way to do it? No. You have to do it the same way every time. You look at this list, and then you say, well, I've got these formulas. This formula matches that list. So if you look back at your formula chart, you're going to see a formula that looks like this. Are we going to use that exact equation?
No.
No. What are we going to do?
Delta y.
We're going to use, to find time, we're going to use delta y equals v naught y time plus 1/2 a y t squared. Time is a scalar, not a vector. Tx and ty don't have any meaning. Okay, now it's pretty much just plugging in and solving, right? What's delta y? 36. What happens to this whole term right here? Oh, it goes away because it starts off from rest, so that's kind of fun. Otherwise, we'd have to do the quadratic formula, which is never fun. Let's see, what's a? 2 meters per second. T squared. Now, you can mess up on the math here pretty easily. What most people find the most success at, simplify this bit first and then divide. If you try and put the whole thing into your calculator, you're often going to make mistakes. That worked out nicely. 36 equals t squared. So what's my answer? 6. How did you figure that out? You've got to do the square root. It's very tempting to be like, I got this, I'm doing this is great, I'm getting to a time, okay, I solved for t squared, I'm done. You're not done. You solved for t squared. Solve for t squared, and then do the square root of both sides to actually get a value for time. In our case, that value for time was a nice round number. In a lot of cases, you will, of course, have to use the calculator. Don't freak out by that. Now,
Wait, so if we put the square root and we don't, like, if it's not a nice number, if we put square root, like 30.
get a decimal. Get a decimal in this unit especially, because this is not normally going to be the final answer you get in the question. Okay, so now we come to the issue that Blake jumped ahead of me and pointed out. This is a river, not a lake. And Blake, what do rivers do?
Flow.
They flow. So this boat is going to be carried off to the right by some constant current.
Oh.
And I'm going to say that this current has a value of 0.5 meters per second. Okay? So, now what?
Now you do the X stuff.
Now we're going to have X stuff to deal with as well. But before we even do that, we don't quite have the conceptual tools that we need to actually solve this. We have to do a little bit of debating first. The question we have to answer. We just found that without the current, the boat took 6 seconds to get across. The question I would like you to answer is, does it take less time, so less than 6 seconds? This is with the current. So with the current, does it take less than 6 seconds? Does it take exactly 6 seconds? Or does it take more than 6 seconds? I want you to talk to the person next to you and get a consensus. Figure out how much longer or shorter or if it's the same.
Shorter?
Like, go like this.
I'm trying to do equal, so you can always have 3.
Goes down.
It's going to be equal time. So one of us is going to be right.
To make sure it keeps going it's just gonna go and then the current
I think it's longer.
Is this one?
Okay, so maybe before we answer,
I feel like that's actually around horse.
something that you might find helpful, the motion initially, what's it going to do without the current? It's just going to go straight across to the other side. What is it going to do when the current is there? It's going to move to the right while it's moving this way. Now, I'm going to put something up on the board, and you'll be like, wait, why does it look like that? We're going to get to that. Don't worry. It's going to do that. It's not going to be a straight line. It's going to be a curve. It's going to be that curve. So don't worry about why it's like that. Don't freak out. Raise your hand if you think the value is less than 6 seconds. Raise your hand if you think the value is exactly 6 seconds. Raise your hand if you think the value is more than 6 seconds. Okay, so why do we think more?
Because it's pushing to the
Okay, so it's going farther. This line is clearly a longer line than the first line. But think about the speeds. Is it going the same speed as it was before? Yes. No. It's got a horizontal speed now, too. It's got a horizontal speed that's going to combine with this speed, and so it's actually going to be going faster with the current than without the current. Not faster forward, maybe, but it will be going faster. Now, we're going to put that in our back pockets for a minute, and we're going to play with this little doodad. It's one of my absolute favorite demos. What it does is I pull back this little notch, something sticks out here, something goes in here, then I go like this, that notch goes away, this pushes out. And so if I take 2 marbles, I would take any number, I put this marble right here, and I go like this, it falls basically straight down. It bounces out to the right a little bit, but it pretty much just falls straight down. If I put the other one right here, it launches out. So the question that I'd like us to answer, which one hits the ground first? If I put them both on at the same time, and that's the real magic of this thing, is that I put them both on, and then I flick this lever, which one will hit the ground at the same time? Now, we are able to hear this. We don't have to see it. You're able to listen. But which one is going to hit the ground at the same time? What do we think?
That one's going to hit first.
So we have the one that's being dropped and the one that's being shot. Which one's going to hit the ground at the same time? That's the question we have to answer.
I'm being shot.
3, 2, 1.
Oh,
Did it really though?
I feel like it was the same.
same.
I'm going to pull it back all the way to the 4th notch.
Oh my God.
3, 2, 1. Listen. Now,
That one.
that one is a clunk clunk. It's very, very difficult to actually make this balanced correctly so that it does that. But when most people imagine that, they imagine a relatively significant difference. Was that a relatively significant difference? No. Where's my marble? That is the worst thing ever to have happened. Now, I'm going to find that. We have 2 separate motions going on. And we're going to come back to this problem, leave some space in your notes for this problem. But we're going to skip like this amount of stuff and then do a little bit more thinking right here. We're going to draw the marble. The marble launcher, we're going to draw what's going on there. And we're going to talk about what those motions are. So, your first task, this marble right here, what did this one do? It fell. I want you to take 20 seconds, talk to the person next to you. I'll try to find my marble. Talk to the person next to you. I want you to describe the motion, be very detailed, and explain why that was the motion. Why did what happened happen? So say what happened. You don't have to write it down. Just talk for now. Say what happened and say why it happened. Those are your 2 goals. You have 20 seconds starting now.
Fell in a downward position.
All right, that's time. So, describe. Who would like to describe for me the motion of this marble? What you got?
Is it just going like straight, like slow, but like straight down? Not slow.
Okay, so it's falling straight down. Describe the speed.
Like, like.
It doesn't ever speed up.
I don't know.
What happens when you drop something?
It gets faster as
It's going to get faster and faster. So we can say that this one is accelerating down, straight down. What's causing it to do that?
Gravity.
Gravity. Okay, so we could describe this motion as gravity accelerates it down. Gravity accelerates it down. Suppose you put an arrow on there. And now we've got the other one to talk about. I'm going to give you exactly twice as much time. There's a reason it's exactly twice as much time to describe the motion of the other marble, the one that is shot. Now, when do I start caring about the motion? Do I care about it when it's just sitting there? No. I care about it right after it's shot. The actual shooting bit, the plunger hitting it, I don't care about that. I care about right after it leaves and right after it gets shot. So I want you to describe that motion, the what, and the why. The why it's happening that way. Go.
So it's gonna go like. It's gonna go out.
Force being applied to
I haven't lost my marbles yet.
Gets more negative. Yes. Yes.
Oh,
So yeah. That's fine. Okay.
All right, that's our time. Who wants this one?
Megan has it.
Megan. It's the same.
It falls straight down.
Gravity accelerates it down.
Force is
Okay, so it goes in a curve. So you're saying it goes which directions?
to the right, down.
Okay, so it curves to the right and down. So let's see if I can do that.
Down and right.
Okay, down and right.
On
Why is it moving right?
because it had a force.
The force.
Say what you said again, exactly the way you said.
It had a force applied
It
to it.
had a force. Is there still a force pushing it forward? No, but it had one. And so that force is going to cause it, that force made it start moving to the right. And so what is it going to keep doing? It's going to keep moving to the right. While it's moving to the right,
It's getting faster.
there's another force. What force? Gravity pulling it down. So we could say that this marble, moves to the right. Leave a little bit of space next to the word right. While gravity accelerates it down. It moves to the right while gravity accelerates it down. Talk to me about the motion. Let me say it this way. Talk to me about the x velocity. Talk to me about the horizontal motion. How does that change as it's going forward? Does it speed up, slow down, or stay the same for going forward? Not going up or down.
Slows down.
So I have all three answers.
It slows down because it doesn't go down.
If we wanted to change the motion of something to cause an acceleration, what would we need? Vocab word, please.
The opposite force.
An unbalanced force, some kind of outside force to change the motion. Is there an unbalanced force that makes it start moving? Obviously, it starts moving, it changes the motion, so there's that little plunger hitting it. After it's flying through the air, it's now flying through the air, going forward, down, yes, but going forward. Is there anything pushing it more forward while it's flying through the air?
No.
Is there anything pushing back against it?
No.
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 So is there anything to change the x velocity?
No.
No. Is there anything to change the y velocity?
Yes.
Yeah.
Yes, but not the x velocity. So it moves right constantly. What was your question? Abby?
No, I was about to ask you about that before you.
It moves to the right constantly while gravity accelerates it down. So, what determines the time that it takes for it to fall down to the ground?
Why?
The X.
It is one of those. You are correct. It is either the x or the y. Let's answer the question this way. Did changing the x motion affect the time?
Wait, did it?
No. Now remember, I can't do it perfectly, so there's gonna be a little bit of a kathunk there. But they hit it basically the same way. If I did that perfectly, they would actually hit at the same time. When I didn't pull the thing all the way in, they actually did hit at the same time. So let's go back to the boat. Is that 6 seconds that we got for going across, is that going to change?
No.
No, it's not. That 6 seconds applies no matter what the current is. That current can be 400 meters per second. And it's still going to go across in 6 seconds. Assuming the boat doesn't break, I guess. So, your part B for this question. Part A was find the time. Part A was find the time. Part B is now figure out how far to the right it moves. Figure out how far it drifts right. So we're trying to figure out how far it drifts right. The first kind of obvious question to ask, which way is right? Meaning, is it x or y?
X.
It's the x. So should we still use our y variables?
No.
No, now we need some x variables. So instead of having a list, we now have a t-chart. We now must make a t-chart.
Can you not do
Is the
a
velocity
list?
constant?
Like, can you not just like separate them? Or are you just like, do you want to do
You should make a t-chart. Yeah, make a t-chart. Say again?
Is velocity constant?
Yes, but don't think about it like that just yet. Like it is. It completely and totally is. But you'll have most people have better results doing it this way. So let's think about what we know on the x side. In other words, ignore the y motion. Just focus on the x side. At the very beginning, the instant we let it go from the dock, what is it doing in the x direction? It's not accelerating. It's moving. The current carries it. Once we let it go from the dock, the current instantly starts carrying that boat. So we have an initial x velocity of 6 meters per second. What else do we know? Come on. What is the displacement?
36 meters.
Is that 36 meters left or right?
Up.
So it's up. It's in the y direction. We don't know the right side. The delta y is still 36, but we don't know delta x. What's the x acceleration? That's the velocity. That's how fast it's moving. Is that speed changing? So it's not very confident. Is it changing?
No.
Zero.
No. So what's the x acceleration?
Zero.
Wait.
How'd you get 6 of the
You know, I honestly don't know where that came from. That should definitely be 0.5 meters per second. I have absolutely no idea where that came from. Okay, so are we cool with that? Have we all mentally fixed my stupid mistake? The one that was on video?
How does it go straight from, like, in the x direction? How does it go straight from 0 meters per second to 0.5? Does it have to accelerate?
Just does. There is a very brief period of time in which it must speed up, but mathematically it's negligible. We don't care about it.
All right.
It's not. If we actually accounted for that, it wouldn't affect our final answer almost at all.
So there's no acceleration?
There is no acceleration. It goes 0.5 meters per second only. That's all it's doing. There's no force in this direction. There's no motor pushing it this way. The current is just moving that way. Do we know the time over here?
6 seconds.
We do. It takes 6 seconds to go across.
No.
It took 6 seconds to go across the river. It's going to take 6 seconds to go across the river. It's the same time for both of them. Time is time is time is time. So now we look over here and we think, well, what equation has those 4 things in it?
The one at the top.
The same one that we used earlier. Delta x equals v naught t plus 1/2 axt squared. That equation is going to come up relatively often. Not every time. You're not always going to use that equation. You are going to use it very often. You're almost always going to use it for the x direction.
Can we use the
Don't ask the question about that, please. Just keep it in your head. Okay, what can I do with this guy?
Put the numbers in.
Okay, so I can plug it in, I can get rid of that whole term. Now I can just solve for delta x. Delta x is equal to v naught, which is definitely 0.5, and then time, which is 6. So delta x is 3 meters. It goes 3 meters right. It drifts 3 meters right as it crosses.
Whenever you make the t-chart, are they always going to be the exact same variables but different directions?
A lot of the time, yes. Not always. One thing to say about this unit is that you're going to very often want to say, is it always going to be like this? And I will say a lot of times, but not always. You have to be on your toes in this unit. All right, I want to do another problem. But this problem is not going to be a boat on a river. So to be a little bit more realistic, it's going to be exactly what you just saw. Me launching a marble. I'm going to launch a marble from the height I was holding it at 6 meters per second. I am about my hands that is, we're about 1.5 meters off of the ground. What I want us to figure out now is how far does the marble go? How far does the marble go? So now I would like you to take a little bit of time, talk to the person next to you. Don't try and do it all by yourself or all in your head. You must get something down on the paper, however. I want you to write down all the givens you can. Write down everything you can. The first thing you want to do is that t-chart. We want to have our x stuff and our y stuff, keep them separated. And now I want you to write down everything you can. You have 5 numbers. You know 5 numbers in this problem. You know, I am very sure, yes. You know 5 numbers. At least one of them will be 0. But you know 5 numbers. 0 counts as a number. So try and figure that out. Get down everything you know. Be careful to separate your variables. Just like before, or just like always, I should say, talk to the person next to you, see what they think, compare your t-charts. No. No. Questions like these are always right before it is. And so we don't know how fast it's going. You were looking for delta x. Now you may be looking for delta x. That does not count as one of your 5 numbers. You don't know that. I know. Physics is stupid.
How is that not?
It's a thing in the t-chart, but you don't know it. You know 5 numbers. Let me rephrase that. I know 5 numbers. I would love for y'all to know 5 numbers too. There are 5 numbers you can know. Do we feel like we're at the limit of what we actually do know, though?
No.
It's hard to do the x and the y separate.
It is. You are completely right. That is what makes this unit challenging. One thing I will say though is the more of these that you do, they're going to look more.
Yes.
I got it.
So you can take a little bit.
Is that like delta x that we don't know? And
For which one? For X?
for x,
Yeah, I thought.
Oh,
I thought
yeah,
so.
5 numbers total, not 5 each.
And
My
Okay,
goodness.
that one.
You do not know literally every number there is to know about this.
Oh, you mean like 5 numbers for
So
X?
is
Yes.
Oh my, I thought you meant like.
Wait,
No. 5 numbers total. 5 numbers total.
This
Okay,
one,
who would
the
like to
initial
give me, I'm going to call us back together. Who would like to give me a number, meaning what the value is, what the number is, and then most importantly, what side of the t-chart it goes on? What you got, Mackenzie?
For the x side, the acceleration is 0
Okay, the x acceleration is 0. That is a bold claim. Defend it.
because well, it's not like it's constantly like the push or like the force going this way is constant because you said it was constant before.
Okay.
And
What
then
would we need to cause an acceleration?
the unbalanced
An unbalanced force, right? After it's fired and flying through the air, is there a force in the x direction? No, we automatically put that down. There is no force in the x direction. By the way, we totally ignore air resistance in this class. It's not a thing. So now we move on to the y direction.
Oh, that's what.
What's the acceleration in the y direction? Anybody have that?
9.8 meters.
Almost.
Negative.
Negative 9.8
Oh.
meters per second squared.
Yeah.
Okay, anybody have another one? Someone who hasn't given me an answer yet, please.
On the x, the velocity is 6 meters per second.
Which velocity?
What do you
Initial or final?
Initial.
Okay. The initial x velocity is 6 meters per second.
Wait, how? Okay. Oh.
That is all horizontal.
The final x velocity is also 6 meters per second.
You are completely correct that it is, but I'm going to leave that off of here for now.
So you don't have to know that?
We actually don't. What else?
You're looking for the x displacement.
We're trying to find delta x.
But we know the displacement is 1.5 meters.
Is that the y or the x displacement? Okay, so delta y equals
1.5 meters.
almost
Negative.
y negative 1.5 meters.
Because it's going down.
Ah, it's falling down. So delta y is negative. If I had to pick one mistake to fix in this entire unit by snapping my fingers, it would be that one. I see lots of points missed because of that missed negative on stuff falling down. It's very easy to make that mistake. Just remember that displacement is final minus initial. Its final is 0, its initial is 1.5. 0 minus 1.5 is you negative 1.5. We know one more number. What's 0?
Initial for y.
Initial velocity of the y.
Okay, I left the hole in that spot, so clearly that's the thing that we know. Prove it. Which way is it being fired?
This way.
Right.
That way, to the right, horizontally. If it's fired horizontally,
There's no.
what is it not fired?
Down.
Up or down, right. Now, watch my hand. If it's fired this way, is there an initial vertical velocity?
Yes.
If it's fired this way, is there an initial vertical velocity?
Yes.
If it's fired this way at the beginning, is it moving up or down?
No.
Will it later move up or down?
Yes.
For sure. But it doesn't at the beginning. I find the weirdest things funny. It's not initially moving up or down. It does that later, it's not doing it yet. So,
Wait, so
We-
we know 6. Oh, wait, never mind. That's just, yeah.
now we look over here, we try and make an equation. Do we have an equation that has those three things and only those three things in it? Unfortunately, we do not. I'll go ahead and spoil the game. We do not. So whenever you get to this part in a physics problem, there are one of two choices. You can either give up and cry, or you can accept the fact that it is a multiple step problem. 2, 3, 5, 20, whatever. You can accept that it is a multiple step problem.
So wait, we have to find time for the first for y.
Ah, you are one step ahead of me.
Yeah.
Clarissa is suggesting that we find time. Well, can we find time in the x side? Can we find it in the y side?
Yes.
So let's do it. Our first step is going to be finding time.
So even if it doesn't ask you to find time?
That is correct. You will need to figure out what to do. You'll need to figure out which side you can work with.
How did we know to find like time?
Okay, good question. There's another variable that we could find on the y side. What other variable is not in this list aside from time? Final velocity, right. Would knowing how fast it's moving down help us on the x side at all?
No.
It wouldn't. It really wouldn't. And so we could totally find the final. Some of you might go do that, but then you get to the point you're like, okay, well, crap, what do I do? You're done. You have to go back and find something else. You've reached a dead end. So we find time on the y side. We put time in our t-chart so we can make a list. What has those four variables? That same equation. How exciting. What happens to that first term?
Just cancel that.
It goes away. We're left with 1/2 times negative 9.8 t squared. 1/2 times negative 9.8 is negative 4.9. Okay, now I want you to watch up here real quick because lots of algebra mistakes are made right here. What do I do over here on the right side? I'm going to divide by negative 4.9. And so we end up with negative 1.5 over negative 4.9 equals t squared. I know a lot of you do this in fewer steps. That's fine. Watch what I'm doing, though. What do you have to do right here?
Cancel the negatives.
The negatives are going to cancel out when you put it in your calculator, right? And then next, what are you going to do? Have you found time yet?
Square root.
You're going to have to square root that. Well, what's going to happen if you forget this negative on the negative 1.5? Is this going to end up being positive? No. And so what is your calculator going to tell you?
Error.
It's going to yell at you and be like, wait a minute, that's not a thing that happens. If you end up in a problem for projectile motion with your calculator yelling at you, there's a good chance you forgot a negative somewhere. Go back and double check that your y acceleration is negative and that your delta y is negative if it needs to be. It's a very common mistake. Anyway, what do we get for time? 0 point. It's definitely 0 point something. I'm pretty sure it's 0.5. 0.57 seconds. Did we solve our problem? Are we done?
No.
Unfortunately not. But we did find time, and what can we do with it? We can use it. The whole reason we found it is that it's going to be another step for us. So we're going to come and write it over here on this side. And now we're going to actually use it. We're going to solve something using time. What equation do we have that matches our list over there on the left? The same equation that keeps coming up. The same equation?
Well, we have to make it extra.
We're going to throw some X stuff in there. Solve that delta X for me real quick, please.
No, like the camera was gonna pop up. It's like no, but I need the top. I need it right now.
Okay, blah, 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 plug stuff in. AX is 0, delta X equals 3.42 meters. If you got that, well done. How do we feel so far?
So basically, we're going to use that equation for all of these.
Not quite. Not on all of them. I will say, you are going to use this equation on probably about 75% of projectile motion problems somewhere. You won't always have to use it, though. You won't always use that equation. Depends on what the problem is.
Castle.
You are correct. Try to think and draw at the same time.
You're gonna launch a bomb one day.
We done cracked your whole question, Mr. Brown.
Go ahead and sign for this.
No.
Cool. Okay, so we've got we have a castle. A calculator. This castle is right on the edge of a bay. And in this bay, there is a pirate ship trying to attack the castle. There's a pirate ship trying to attack the castle. We're going to try and deal with that by, most of you have already guessed it, a cannonball. Unfortunately, the cannon makers of this castle are not very good at their job. They have made cannons that only fire horizontally. They cannot be angled. So, obviously, they're going to fire a cannonball of some unknown velocity, and what do they need to do?
Angle it down.
Well, they can't angle it down, it's a bad cannon.
They have to make it not shoot as hard.
Well, they have to figure out a way to make it shoot the ship. They have to hit the ship. That is the statement I'm trying to get y'all to make. They have to do something to make that happen. They have to make it hit the ship. Now, this pirate ship might be moving. What is the cannonball going to be moving faster than the pirate ship?
Yes.
Obviously. Because it's moving so much faster, we can ignore the velocity of the pirate ship. There's no way the pirate ship can dodge that cannonball. Cannonball's going too fast. So we're going to ignore the velocity of the ship. What we're trying to find is how fast they must shoot. And we need to know a few things. Luckily, the people who built this castle are better at castle building than they are cannon building. And so they know that their castle is exactly 75 meters tall. It's about 8 or 9 stories. And then, you know what a sextant is? A sextant.
Not really.
It looks kind of like a protractor with some weird magic levers on it. You look through it, you point it at something, and it can tell you what the angle of that thing is. They use one of those, and they figure out this pirate ship is 150 meters away.
But yet they can't make a good cannon.
Sextants are easy to use.
We made one in history.
Okay, our task, I say your task, figure out how fast they must shoot the cannonball. Obviously, you're going to make a T-chart, and then you're going to solve, it will be a 2-step problem. Feel free to go back and look at the problem that we just did, and feel free to talk to those around you. Okay, I'm going to pull you back up here. I am seeing some absolutely fantastic stuff, loving it. Because I've seen a good T-chart on basically everyone's sheets, I'm going to go ahead and rapid fire through this. Somebody give me the x acceleration.
0.
What about the y acceleration?
-9.8.
Negative 9.8 meters per second squared. Again, there is no x force. There is only gravity as a y force. Okay, what about the deltas? Delta x equals
Question mark. Oh,
150 meters. Delta y equals, careful, negative 75. How many of you made a mistake on that the first time? I saw lots of positive 75s on papers.
No, I don't.
Okay, what else do we know?
We know the initial
Initial
velocity.
for y is 0.
V naught y is 0. How do you know that V naught y is 0?
It's not moving up or down yet.
It's not moving up or down yet. It's moving forward for sure. It is moving forward, but it's not moving up or down. It's only moving forward. Okay, good. So we do the same thing. We look over here. We think, we say, do I have a formula that matches those?
No.
Unfortunately not. So we must now look at the other side and think, what can I find over here? We can find the time. So that's going to be our first step. We're going to find time. What formula matches that list of stuff?
The same one.
Our favorite one. Delta y equals V naught y t. What's going to happen to that term? That's going to go away. What's the 1/2 times negative 9.8 going to turn into?
It's going to turn into
Negative 4.9 t squared. T is eventually going to equal 3.91 seconds.
Oh. Do we have to put the 1?
No. We have now found time. We will now
put on that side.
use it. We will use time.
Find the initial.
Okay. What formula has this stuff in it?
The same one, the x direction.
Okay, that same one, but now we're going to make everything be in the x direction. What's going to happen when you use this formula?
The 1/2 is cancelled out.
the 1/2 AT squared all poofs and goes away. Isn't that right, Blake? Because the acceleration there is 0. And so now let's bring this back together. Let's solve for the x velocity in variables. We get delta x over t. Look familiar? Yes. When are you allowed to use that equation? When velocity is constant. Is the velocity constant? Yes. If velocity is not constant, does that algebra work?
No.
No, you have to do quadratic formula to find time. That must be 0. The acceleration must be 0, and then it turns into this. You can actually use this for the x motion for something that's launched, but I recommend you start with this. Do that, you will not make mistakes if you do that. There are traps that you will fall into if you try and get fancy. Don't try to get fancy. So anyway, we do that. We plug some numbers in. What do we get? 38.5 works for me. 3 numbers that aren't 0. We're good. 3 sig fixed. So that's that. That's the problem. How'd y'all feel about that one? You just did a problem, mostly by yourself. I helped a few people a little bit, but I didn't help anybody very much at all. You just did a problem that was significantly harder than anything you saw in the first test.
Really?
That is harder than every single problem on the first test. It is. No, the first test, the hardest problems on the first test was like that or that. And now you had to do them both at once. Remember how I harped on you the entire first month of school? It's going to get easier. You're going to get better at it. I know you feel behind now. We're going to come back to it and you're going to get it. This is that moment. We've come back to kinematics and you understand it a lot better than you think you do. This is that moment. Now, we're not out of the woods yet. Physics is still hard. Don't get me wrong. You're still going to struggle in this class. And you're going to feel behind a whole lot. That's okay. We're going to come back to things at the end of the year and throughout the year in other units, and you'll be like, oh my God, I actually kind of get this. We're going to come back and you're going to realize, oh, hey, that actually kind of sunk in. I got that. That's why we have tests and then test corrections. The test corrections are where a lot of the learning happens, and that's okay.
The test is 65 passing, or is it?
For the quiz,
No. For
70's passing. Do you mean what? You mean like on an AP scale? Okay.
You said like a 67 was passing.
On a quiz.
Oh.
You know, how if you pass, you can make it up to a 90. If you pass a quiz, you can make it up to a 90. If it is a 15-point problem, which most of them will be, then 67 is a passing. You don't need a 74. So you need a 10 out of 15, not 11 out of 15.
When do we start test correction?
Test corrections, I am waiting. Both Mr. Ayers and I are waiting for everyone to take the tests. We can't give the key out until we've got the test taken care of.
Was there
I can tell you that.
I know.
It's like 5-ish. The number is slowly going down. Okay. I would like to make a little tips and tricks section. This is a very valuable thing in this unit specifically. Just tips and tricks. So we're making some tips and tricks. Anytime I ever do a list like this, it is often different as I go class to class. So definitely leave some space afterwards. There's a very good chance I want to come back later and be like, hey, remember that list? Let's add this to it. Or we're going to do a problem and be like, hey, let's add this to this. Because of this problem, let's add this to our tips and tricks list.
It's only for this unit.
This is for this unit, right, for projectile motion. Tips and tricks for projectile motion. There is one thing that we should definitely start with, every single problem.
Time.
No.
The acceleration chart.
We're going to make a T-chart. Now, I'm going to write stars up here. You may put in whatever word you like. Whatever word you need to use in your notes to make sure that you write a T-chart, that you make a T-chart. I don't care what that word is. By the way, if the principal comes in, the word is good. Make a good T-chart. But you may put whatever word you like. I will not read your notes. I want you to make a T-chart. You must make a T-chart. You are not smart enough to not make a T-chart. You must make a T-chart. And then, Blake, what was your suggestion about another tip and trick we can put up there?
Time.
Time, right. A lot of projectile motion problems involve find time and then do what? Use time. Use time, right. We find time and then use time. Does that always apply? No. So we should probably put it usually right there. But if all else fails, start finding time and then using time. Okay? What else? Think about the last problem that we just did. Think about some ways you could have made a mistake.
The negatives.
Okay. So what was negative specifically?
What the
Everything in the y
acceleration?
direction going down.
Okay, so things going down. Specifically that delta y. I want to throw in that bit about the delta y. When is delta y negative?
Going down.
For something going down. When it ends below where it started. I'm going to put this as falling down. There are lots of different ways that something can fall down, though. If I drop it, is it falling down?
Yes.
If I throw it down, is it falling down?
Yes.
If I throw it down at an angle, is it falling down?
Yes.
What if I, from my hand up here at shoulder height, throw it up at an angle? Is it falling down?
Yes.
Yes. It's just moving up in between. All of those represent something falling down. All of those represent something ending below where it started. So the delta y is going to be negative.
Okay, so on a problem where it goes like this, would we be given
The height of the cliff, yes. The height of whatever it's being launched off of. You mean like
would
this
the,
height?
Would the peak of that be significant?
Sometimes, but very rarely. What else? What else can we write down that's often true?
Sometimes like the acceleration will be 0. Something like on the X.
We know the acceleration and the y acceleration 95% of the time. Anytime, I will tell you this, anytime something is being launched through the air, on Earth I should say, on the moon this will not be the same. If it's launched, ax equals what? 0. And ay equals negative 9.8 meters per second squared. If you are on the moon, is ax going to change?
No.
Is ay going to change?
Yes.
Yes, the gravitational field strength pulling it down will be different.
Would it be lower?
It'll be lower, yeah. It's about 1.6 instead of 9.8. Okay? I can think of one more.
The formula.
The thing, I don't want to make that a tip and trick because the only reason we've used that one is because of the problems I've given you. I could give you problems that wouldn't use that.
The velocity initial for 1.
Is what?
0.
Always.
Well, only if it's
Is it 0 right here?
no.
Is it 0 right here if I drop it? Not if I throw it, if I drop it.
Okay.
Yes. Is it 0 right here?
No.
Is it 0 right here?
No.
Is it 0 right here? If I shoot it horizontally?
Yes.
It was 0 earlier. So what makes it 0? When is v not y 0? When it's a horizontal launch, when it's a horizontal shooting or throwing or something. If you see that something is blanked horizontally,
Is what?
something, thrown, shot, launched, something horizontally.
Okay, so what if it's at like a horizontal angle?
Then you will have to find v not y. You'll have to find it.
Mr. Brown, the last one, if we were, I don't know what, would it be significant, like the arc? I don't understand why we wouldn't need the arc height.
Why you wouldn't? Math. It depends on the problem. Sometimes you'll be asked to calculate it, but the only reason that you would be given that value is if you were going to use it for some tricksy problem. There's not really like a deep physics reason why you would ever need to be given that. We're going to leave that. We'll come back to that. What I want us to do now is gather around. We got a little demo. Now it's recording. Okay, so we've got a problem with a cannonball that's launched at 30 degrees at a speed of 40 meters per second. It's being launched and it's landing back on the ground. What is the first thing we're going to do for this?
Make
Make a blanky blank T-chart. Right. We're going to make a T-chart. What are some things that we know in this T-chart? Okay, what's the velocity? Is that Vx or Vy? Okay, so it's Vy because it's going up, but couldn't you say it's Vx as it's going forward?
both.
It's both of those. Both, no, don't write. The velocity is in both directions. If you want to find Vx or Vy, you must make a triangle.
No.
Now, guys, this has not changed at all. Physics is still physics. Trigonometry is still trigonometry. Does it matter if that says 40 meters per second or 40 newtons? No. Evan, wake up. It does not matter what units that is written in. All that matters is that the trig is the same. Okay, so Vx. Is Vx the opposite or the adjacent? Remember, that's the question we care about. It's the adjacent, so I can immediately write down what?
Cosine.
Not cosine. 40 cosine
VX.
30. Thank you. Good Lord. Okay. Vy, is it the opposite or the adjacent side? It's the opposite, which means get this one right, dang it. We can immediately, no, not sine. We can immediately write down 40 sine 30. You need the whole thing. Even if you are terrible at trig, that is okay, because you will either write down 40 cosine 30 or 40 sine 30. You must just know which one of those to write down. You should also know the sine of 30 degrees. It's what?
I don't know.
1/2. 40 times 1/2 gives you 20. This 34, I want to say 34.6 meters per second. That's for another class. I didn't know that off the top of my head. So we have our Vx, we have our Vy. That's a thing we should probably add to our tips and tricks. We were given a velocity at an angle. So what did we immediately do? Do trig. If you see an angular launch, before you do anything else, before anything else happens, do the trig first. Break it down and do the trig. Do your trig first. Okay. What else do we know? Give me the easy ones. What do we pretty much always know? Something launched. Ax is 0. Ay is negative 9.8 meters per second squared. We're trying to find here delta x. You know that because I just told you. We know delta y. We know a number for what delta y is.
So it's x is 0 even though it's being launched.
Don't worry about the launch. This is after the launch. While it's in the air, there's no x force. Now, remember what I said. Ignore the height of the cannon. It is a tiny little cannon. Compare the height that it lands to the height that it starts at. It's the same. Remember, we're ignoring the height of the cannon. That is the same height as that. Since they're the same, what is delta y?
-40.
0.
Oh, just kidding.
Delta y is 0. It is a symmetric launch. It starts and lands at the same height. I would consider that a pretty good tip and trick.
Oh. Does it start?
Will it tell you like it's a symmetric thing?
You will figure it out from the problem. In other words, it will say it is shot and lands on the ground. There will be a picture. There will be something telling you that it starts and ends at the same spot. And if it starts and ends at the same spot, if it's symmetric, delta y equals 0. So our delta y equals 0. Now, we are trying to find delta x. We know the basic pattern of these problems. Can we figure out delta x over here? No. So what are we going to do first? We're going to find time. Don't put your things away yet. I want to get through this. This is important to get through. A lot of mistakes are made on this specific thing. What equation are we going to use with that list? Yeah, that's actually not the regular one. The one we use a lot. Not the one we use always, but the one we use a lot. Okay, so we get that. is it going to look the same as it always does?
Please pardon this interruption for an important announcement.
Oh.
Attention 9th, 10th, and 11th graders. The PSAT
Is this going to cancel out?
You
No.
may have seen your teacher
This
reading
is, though.
poster boards around their
So we
desks
say
last
0
week.
equals,
They were advertising PSAT strategies.
Oh
For
my
example,
gosh.
what's your POOD? POOD is your personal
and so a
order
lot of
of
people look at that,
Read the
and they
passage.
immediately go, oh no, quadratic formula!
For you.
We will eventually have to do the quadratic
Complete
formula.
first and come
This
back
time,
again
we
to
actually
navigate
don't
those
have to.
more difficult questions.
Check this out.
The
I'm
reading
going to
section
subtract
is
20t
open
from both sides.
You can't put your
Please
finger
don't
on
work
every
in front of me on this problem
passage or your
specifically.
answer,
Stay
then
with
it's
me.
not the answer.
These
PSAT
steps are
tests
often
your ability
missed.
to use concrete evidence
Negative
to support an
20t
answer choice.
equals
Commit.
negative 4.9t squared.
Bubble an
I
answer
need to
from
be
every
100%
question.
sure.
Omit
I know that there are distractions right now. I need to be 100% sure that we feel good about this.
POE.
How do we feel about me subtracting 20t over to the left side?
Physically cross out the answers you know to be incorrect. If you move on and come back, at least you've already completed part of the task.
That is this.
This makes me so
RTSQ,
happy.
read the full question.
20, yeah,
Math
this
problems
g not y
may
is
be
20,
outrageous when you
so
first
that's
begin to
20t.
problem, But if you read the full
And then
question,
20t
you may
gets
very
subtracted
well
over to the
discover
left side.
it
But the
wasn't
reason
that
I'm doing that is that
difficult after
zeros
all.
are awesome. Zeros almost always mean that you
Plan to
can
spend
cancel
approximately
stuff
1
out.
minute, give or take, on each question.
We're not done yet. No, we're not done yet.
This test was
We're not. We're at 8.
tricky. So use these
Oh my
strategies
goodness.
to help
We're not.
you
Guys, I know this is crazy. Follow along.
Defeat the
We're
game.
not quite done yet.
Remember, a high score on
Can we
this test
cancel
gives
t
you big
squared?
bucks. Cha-ching.
Can we
Eat a good
cancel
night's
t?
rest, Eat a good breakfast.
Yes.
And
This is the same as writing negative 20t equals negative 4.9 times t times t. Can we cancel out both of those t's?
No.
No.
We can cancel out one of them. The way I'm almost always going to write that is like this. Divide by t, divide by t. And so now we end up with negative 20 equals negative 4.9t. Is that solvable?
Yeah.
For sure. Does anybody have a number for me, by the way?
4.08.
4.08, thank you. Okay, now let's imagine a world. By the way, we know the next step here, we're going to use time. Let's imagine a world in which your algebra skills aren't very good. You try to do number 1 and you get your T-chart down, you plug your numbers into the correct equation, and then you're like, oh my god, I know Mr. Brown taught us how to do this, I cannot remember. I have no idea what to do. Make up a number.
Seriously?
People always think I'm joking when I say that. BS some algebra and get to an answer, put it in seconds, make up a number. Write down t equals 5 seconds, whatever your favorite number is. Because the way part B is going to be written on a free response question. It's going to be, plus 1 using the x component of velocity and not 40. Plus 1 using the correct equation. Plus 1 correct substitution from part A. It will not say plus 1 using time equals 4.08 seconds. It will say plus 1 using the correct substitution. If you make up some dumb number and then use that dumb number correctly in part B, have you done that?
Yes.
Yes, you will get the point.
Nifty.
If you're bad at algebra, that's okay. Make up an answer. Never leave an answer blank. A lot of times, the 15th point in free response problem says there is an answer in every single blank, and every answer has correct units. If you have all of those, you get that bonus point. If not, you don't. Always make up a number if you can't solve a mathematical answer. Okay, that's it. Put your things away. You have homework. Remember, your homework is due Thursday. You guys are going to be the first class from now on. You're going to be ahead of 8.